board, and then, okay, great.
Okay, so hi, my name is John Joe. For those of you who don't know me, I graduated undergraduate from a different university, and I took classes here the last 2 quarters. So I'm like an active visiting student right now. So this work, so how I got involved with it, it started when I was an undergraduate. So we did like a little project, and then it was kind of over and finished even before, or it started and was finished even before I took undergraduate quantum mechanics. So I just randomly at the end of the summer, or at the end of the spring quarter, I contacted my old advisors who I was close with, and they were interested in this problem again. And then I figured, okay, let's do this. And a lot of interesting things are coming out of here. Yeah, so I'm pretty new to the subject. It'll be nice if everyone could contribute what they know, if they know something. So if they have anything to share, yeah, please do. I'm still learning. I've been studying this for maybe a month or two, or yeah, about then. So okay, so the outline of my talk, I'm going to start with the Casimir effect and tell you what it is, some possible misconceptions, how it's being calculated, and then I'm going to go to an area called the repulsive Casimir effect. And this is really, it's lacking. It's not only of interest to people in material science or condensed matter physics, but it's lacking a fundamental explanation. It's pointing to a fundamental misunderstanding of the quantum vacuum fluctuations. So we'll start with a result by Boyer between an electrically conducting plate and a magnetically conducting plate. They're perfect conductors. So this is infinite electric permittivity, and this is infinite magnetic permeability. And then I'm going to go on to a case where if you have a conducting plate with a hole and you put an elongated metal needle on it, the needle will get repelled to a certain distance and it'll get attracted. So this was done. This is pretty much what we're going to be focusing on during this paper. This was done by Michael Levin, I think, before he came to UChicago. So it's a coincidence that I'm getting involved with this project, and he's also in the department. And I'm going to discuss some new findings, how strange this situation is, and then what is new about the repulsive Casimir effect, different areas of repulsion in the situation where we take a dielectric kind of disk. Okay, so instead of the perfect conducting, we replace a perfect conductor with a dielectric material, and we replace a needle with a polarizable atom. And then I'm going to talk about some ways in which we could stabilize the atom, which as of now goes against some generalization of Earnshaw's theorem. So the Casimir effect, it is known as the attraction between neutral parallel plates in a vacuum, and it's still one of the least intuitive concepts in QED. And the repulsive Casimir effect, as you will soon see, is even more non-intuitive. So the Casimir effect has some mantra, kind of like gravity, where macroscopic bodies affect the field and the field acts on the bodies. So like gravity, mass curves space-time, and space-time tells mass how to move. So a typical calculation between two plates will be if you take the stress energy tensor. So we have, we could find the pressure between the two plates as the difference between the energy momentum tensor on this side, and then we could call this z equals a minus delta, and then evaluated at z. Sorry about this. So I was planning to do an iPad talk, like just straight during the iPad, but then a couple of days ago, a statue fell on my iPad screen and it cracked. So I scrambled to my friend's house and created this real quick. So I thought it would still be possible to do this to some extent. So the pressure difference between the two, we have the force over area, and the force in the z direction. We'll call this the z direction. And what Wikipedia, like a Wikipedia article will say, okay, there's boundaries, so there's only a certain amount of virtual particles that could get from one boundary to the other. And there's only some certain modes that could exist. Hovering outside the plates, there's many, many modes. So all different kinds, and then this creates a pressure difference. But then by the end of this talk, you should be convinced that this is not the only thing that's going on, and this isn't a full picture. So, okay, so this is the typical calculation. So let's do something simple. 2D scalar field theory, massive, so one space, one time. So we have this interacting Lagrangian. So we have a scalar field, this in between these two, and then we have these delta function potentials. And if we take the coupling going to infinity, we get Dirichlet boundary conditions. So, you know, it's kind of two one-dimensional object with two endpoints with Dirichlet boundary conditions. So what we can do is we can calculate the Green's function, which is just the expectation value of the two fields, and then, or the same field twice. And then we could take the stress energy tensor, which is just a Green's function at the coincidence limit, multiplied by, or acted on by the operator, the differential operator. So we could take the expectation value of this, and then what we'll see is that the stress energy. Okay, so let's look at this point, and we can see the stress energy tensor. Well, this is just the for the reduced Green's function, and then we integrate this over all frequencies. We see that we have some divergent terms. So K, or kappa, is just mu kappa squared is mu squared minus, and mu is the mass, minus the frequency squared. So we see that on the left of this, we have the left of the material, we have a divergent term, and then we have contribution from this material. And then on the right, we just have the same divergent term. So what happens is they cancel, and then we're left with something finite. And actually, this is from infinity. So y setting right here, y equals 2 kappa, and then the distance. So, and this integral is very nice. It evaluates pi over 6, and we're left with a pressure, a finite pressure. So is there any questions so far? Okay, so I'm going to be talking about the first aspect of the repulsive Casimir effect and how non-intuitive it is. So in classical electrodynamics, we have this force on the boundary of material, and it's given by this equation. So going this way, we see that delta E, or delta epsilon, is 0, or it's negative. So then this should be positive, and there'll be a force going this way. And then likewise, delta epsilon is positive, so there'll be a force going this way. So these two attract. And then likewise in the magnetic case, this attract. And then in the electric, if one is electric and one is magnetic, they both attract each other too. But then, however, when we consider van der Waals force, which is the non-relativistic version of the Casimir effect, we see that electrically polarizable things, an atom with only electric polarizability and an atom with only magnetic polarizability will repel each other. So thus, something that will attract each other in classical physics will repel quantum mechanically. And I will save, I advertise this being that the spectral distribution between the scattering between the two plates, this actually has something that is as a Fermi-Dirac signature, while 2 okay, so I should also say that two conducting, so if this was electrically conducting, and in the perfect conducting limit, so if this is an electrical, if this is a perfect electrical conductor and this is a perfect magnetical conductor, this will yield a Fermi-Dirac distribution. And then if these are both electrical conductors, they will attract each other and they will have some Bose-Einstein signature. But I would like to get to the anisotropic repulsion, which is, I'll be motivating the most interesting parts of my talk using this. So like I said, there was a perfect conductor. And if we have a hole in it and we place this elongated metal needle, so the whole situation has to deal with the fact that the needle is elongated instead of circular. If it was circular, it would there would be no repulsion, but then since it's elongated, it's repulsive to a height h, and then above which it becomes attractive again. So it's repulsive, attractive, and there's a saddle point. It's unstable due to lateral perturbations. So I guess you could see the repulsion in the center. It's still somewhat non-intuitive. A way of understanding the attraction at higher distances is that the needle just sees the plate, kind of like the hole becomes neglected. Oops. Okay. And then the argument given was that there is, at the center of this hole, the needle has zero energy, and then at infinity has zero energy. So that means it must gain energy, and then energy must increase and then decrease, and then there should be a saddle point right in the middle. And it obeys a generalization of Earnshaw's theorem given by these people in 2007. They're from MIT. They're called the MIT group in literature. So, okay. So maybe we could do a little better. Maybe we could find a situation where this is stable. So here this was done numerically because working with this region, if you work with a perfect conductor that's not two plates, it gets very hard to do. But there's a situation where you could actually extract the exact interaction energy from the, if your materials have a weak polarizability. So the polarization in the plate is very weak. And then if, so we replace this with a weak dielectric material, and then we replace the elongated metal needle with an atom, and the atom gets in its anisotropy included by saying that there is only, it could only be polarized in one direction, and well, it could be polarized in the other directions, but they can't equal each other. They must have anisotropic polarizability. So if they're, so let's just say if the atom is polarized in alpha 1 or E11, and then, which is just kind of like this, and then it could also be polarized going this way too, and if they equal each other, then there is no repulsion. And same with the plate. Yep. Hi.
Can I ask a question?
Yeah.
So in your previous slide, so this argument that there's a saddle point, you said, okay, so fine, the energy at infinity is 0, but then you said the energy when it's in the middle is 0. Why is that?
Oh, it's in the middle?
Yeah.
So I guess, so I could, for the perfect conductor, it's not super intuitive for me, but let's just say in the plate example, so if we have the dipole is going up. Okay, so right now I guess it's elongated because the charges could accumulate on the side. So we have positive and negative. And then if we have the same situation in a dielectric material, just kind of mathematically, we'll see that the energy goes to 0. Yeah, I'm not, I think, okay, so it's, you get contributions from, so there is an argument, I believe. I think it's the fact that this is in the middle. So maybe if this is if this is rotated 90 degrees, the interaction energy won't be zero.
I guess the symmetry arguments to me make sense that the force is zero, but I guess the overall energy, why is that the same as that infinity?
Yeah, I think so. Okay, like I said, I think this has to do with the way the needle is pointing. So I think if it's pointed 90 degrees, there will be some energy. The energy won't go to zero, but there'll be some energy, but there'll still be no force. So the force will still be zero, but the energy will the derivative energy will be zero. But yeah, maybe. So this was hard to see because this was all done numerically. But then we'll see a situation. So I have it worked out, calculated, where the situation, if the in this case, if the atom is in the middle, the energy goes to zero. Like the energy will be zero. So we'll see that.
Okay.
Okay.
Okay, thanks.
Yep. Okay. So actually, in this situation right here, sorry. So in this situation, yeah, you can see here by the graph. Oh, okay. So yeah. So like I said, in this situation, Kyle, if the atom is at 0 degrees, it will become. We can see here. We could plot the energy, and we could see that the energy is 0. And it is repulsive, except if you rotate the atom away from the axis a little bit, it becomes 42. If you rotate it past 42.1 degrees, it will become attractive. So, okay, so this is pretty much, there's no new physics going on here with the dielectric plate and the atom. Okay, and then we can do the same thing with different polarization. And this is done because of the weak approximation. So I was going to derive the methods that we use, how we start from the normal energy of the vacuum by using the quantum action principle and varying the fields and seeing how the vacuum changes. But I think I want to, I'm excited to get to how new physics emerges when you consider a different geometry than a plate, like just say a ring. So I want to keep this momentum going. What I would say is that for the weak case, this energy breaks up very nicely, which I could argue this. So the energy of the whole system is given by this, and then we could subtract the energy given by the background field. So this is -1. So this is the free Green's function. So if we subtract the two, we get the energy of the plates, or in the energy of our objects. So we have the energy of object 1 given by this. We have the energy of object 2 given by this. So this is object 1, inverse object 1, trace ln G2. And what we find is for two bodies, we get something that looks like this. And this is the finite piece coming in. G chi G1, the chi 1 for the material, G2, chi 2. Okay, and this is pretty interesting. We could rewrite, motivate this. So we could take, if we look at this as scattering, we could take the total Green's function as a free Green's function plus the free Green's function times chi, free Green's function, and then you keep going, sum it up, and then what we get is we get G naught 1 minus G naught chi. So we could rewrite this expression as trace ln 1 minus G naught, and then we could define the transition matrix, the scattering matrix, as chi 1 over G naught chi. Yeah, I apologize. So scalar matrix 1, scalar matrix 2. And we get a nice picture of, so the interaction energy for the weak case is just a virtual photon that starts at material 1 at one point, propagates to one point in material 2, and then comes back to that same point. Okay, and then that gives us the interaction energy in the weak case. In the strong case, we can't take this very simplified view. So now that we have this, so this was for scalar field. I kind of want to really motivate this, but this is the Green's function for scalar field. We want electricity and magnetism, so the free Green's function is given by this. Okay, I know, what time is it? Yeah, I know that you guys, this is a lot of math, but I'll just kind of motivate the setup, and then I won't go through the math. But so we could model, so let's start with a ring and atom. And we'll see something surprising coming out with this interaction. So if we start with an atom, we can model the atom by the, we could say that it's atomic polarizability. We could just keep it frequency dependent for now. And then we have, we can model it at one point in space. And then we can model the ring. So we have 3 delta functions. Then we have a one-dimensional ring. So it'll give us 2 delta functions. And we consider our atom, we could say, okay, it has two levels and with fundamental frequency, omega naught. And then with, this is the static polarizability. So if the static polarizability is greater than, if the distance is greater than the static polarizability of the material, so the atoms in the ring and the atom in the plate, or just the atom in the ring and the atom above the ring, then A is small, and then we can make this approximation. So now we could also go to the Casimir polar regime, which is just the relativistic version of the Casimir effect. So I actually just learned this. So we could look at something like this. So this is c equals 1, the speed of light equals 1, the speed of light equals infinity. So, and then this is weak coupling. So this is lambda, or epsilon near 1, and then this is epsilon goes to infinity. So we have the Casimir effect up here. So this is the relativistic strong coupling. The van der Waals force is non-relativistic weak coupling, and DARS Waals. And then we have the Casimir polar, which is relativistic and weak coupling. Casimir polar, CP. Okay, and we can make this approximation because the what's nice about this approximation is that we only consider static polarizability, because if it's far away, we need to have very low, the atoms need to fluctuate, and it's have a low frequency of fluctuation in order for the interactions only are the we only consider the low frequencies, since it if it's long range, only low frequencies contribute to the interaction energy. So what we find is when we calculate the interaction energy, we get the same behavior. We get similar behavior for E for when the atom is aligned with the axis as a plate, and then once we saw that once the theta tips to 42 degrees, or 2.1 degrees, we get attraction. But however, for high values of theta with the ring and the atom, we actually find very high up, it's very small, you cannot see it with this graph, but we find another region of repulsion, another repulsive region. So this is very bizarre. And you can see the force here. Oh, this is the energy. Oh, this is for the ring polarized in the same direction. So pretty much you just add pi over 2, and then we get the same results. So yeah, just compared to classical electric dipole, where we have repulsion and then attraction. At this, we get this new range of repulsion, which is very weird. And things get even more weird when we add the disk. So let's see what happens. So we could see what happens by making this, instead of a ring, we could give it some width, and we can model this by, instead of having the delta function at rho minus a, we could have 2 theta functions. And then we see as b goes to infinity, we get a plate. And then as b goes to a, we could do this intricate, there's this little, this limit takes a little bit of work, but we could see that hello. Okay. I died out for a second. I'm back. Okay. So what's interesting about this disk is that not only do we see, let's just say, we consider the outer radius to be a multiple of the inner radius, just for the sake of analysis. So we see that, just for take example, if the outer radius is twice the size of the inner radius, we get this blue highlights the repulsion. So this is theta and equals 0. Right here is theta equals 0, and this is theta equal pi, and this is the height, h over a, the distance of the height above the ring over the radius of the ring. So we get repulsion. This is seen in the plate and in the disk, or in the ring, but then we also get repulsion for high values of when the atom is very far away from the disk. So from here we get repulsion for a little bit, and then we get some attraction, and we get repulsion again. So R, A, R. And then similar behavior. Hello? Okay, if you hear me, could you say something? Could someone say something? Maybe just.
I can hear you.
Okay. Okay, great. All right, so what happens is that for the disk, we get repulsion, attraction, repulsion for low values. And then similar to the ring, we get attraction, repulsion, attraction. So if I could draw this out here.
Hey, Chandra.
Yep.
I think it might help if you turn off your camera. Like,
okay. Sounds good.
Potentially somebody suggested that.
Sure. How do I turn off the camera? Maybe up here. Video.
Thanks.
All right. So let's compare this. So I drew this. So this is for the disk at n equals 2. And then for the ring, just to graphically emphasize, yeah, sorry, like I had so much technical malfunctions. Even the computer that had Mathematica stopped working. This nice computer ran out of space, so I can't have Mathematica. Let's see. So this is for the disk. For the plate, we just have something that looks like this. These are the 2 regional repulsion. And for the ring, we just have these 2. Oops, this is not drawn to scale. And then this. So these pretty much should be equal. Oh, my internet connection's unstable. What's happening? All right, so yeah, so this is, so understanding what's happening here, I think there's like enough data to, I don't know, make some type of conclusion. But do you guys have any questions for now? Is there any questions? What's going on? Okay, so we see, so explaining that this behavior, we see that the disk gets pushed back farther and farther. This regional repulsion. So, okay, I think this is like 1.1, This is maybe 1.2, 1.3, like 1.4, and then on and on. Yeah, we see maybe this is something. I think this is like n equals 2. Yeah, sorry about that. Okay, so yeah, so this is pretty non-intuitive. We think of something that might be happening. So what started our project, so this is why this project stopped pretty quick during undergraduate, but we're still, with these new findings, we could write a very nice paper with this, which is in the process of being published. So, so the proposal was that if we, so let's just say we have this ring and this is theta around theta equals 0 or theta less than 42 degrees, we have repulsion to a certain point, attraction, and then in order to stabilize this, we could consider kind of rotating the atom, kind of like a levitron, or just even a toy top. And I thought that I would be able to say something about this, but then for various reasons, this became difficult. So the reason why there was concern was there's like a sine 2 theta coming in this term. So finding the rate of change of angular momentum to accommodate this, that would be a little tricky. And even the question of what is, what can we say? How does like what's the angular momentum of the vacuum due to vacuum fluctuations? A change in angular momentum of vacuum fluctuations, that's a difficult question to answer. One way is we could look at the full angular momentum, and then we could take the gradient or the del across the stress energy, the energy momentum tensor, and then we just get the green static given by this equation. So in the coincidence limit, we take this, but that is very difficult for objects that don't have as much symmetry, such as a plate. In the plate, this is pretty easy, but then these objects are pretty difficult. I wasn't able to, as of now, I wasn't able to find anything. And I think because also I was focused on this disk, because this was trying to understand this is pretty, that was a focus of mine for this past week. So finding a disk. So, and there's also like taking time into account. So time isn't really very well understood in quantum mechanics. There's a dynamical Casimir effect. So ultimately, this atom should be experiencing some friction, and then also some might create some virtual or some real photons. Some photon production might be created when we. So I didn't write this down because it was a big expression. But then if we move the atom away from the ring or away from the symmetry axis, we see that the force is actually pulls it. So we verified that the atom is unstable at this point. The force in the radial direction keeps pulling it in the radial direction, and the expression looked pretty nice. There's a bunch of hypergeometric functions, which I did not decide to put. So also a couple days ago, my advisor, he suggested this. So this was his idea. We can make something like, I think it's like Rotaxan, which is a molecular machine. So pretty much if there is we have like a molecule, and then we could have a molecule wrapped around this molecule, and then by chemical reactions, this ring could move up and down, and then it could kind of give energy to the system. The system could move. It's like a molecular machine, and then this is of the scale 100 nanometers, which is exactly where our Casimir polar approximation lies. So, and if we consider a rod and we consider the atom polarized at the end of the rod, we consider the disk right here. So this exact setup, and there's a heavy particle on the other end, so that this rod is stable. When theta is equal to 0, the energy, we'll see that the we'll see that the energy is at a minimum point. And then if we rotate this 90 degrees this way, then we give the energy. So so somehow the atom's polarization kind of goes from 0 to 90, and then we give the system some energy, and we bring it up to this point B. And then from there is a repulsive force. So the ring moves from here to height h, a distance h. And then what happens there is it also induces a torque on the atom, the polarization of the atom, and then the ring just falls down. It becomes repulsive or attractive again, and it falls down. And this is actually, so this happens. So for theta equals 90, the region of repulsion over here is over here. So it definitely becomes attractive again. So is there any questions on this setup, on situation? This was kind of I don't know, something to include some ideas. So here we go. We see that the work done going from A to B, we put in work, and then so we do work on the system. The system does work, and then there's no work being done going from C to D, and then there's negative work being done going from D to A. So going from back here where we started. Okay, so something interesting that came out of this was something interesting I learned pretty recently, was that, so let's really consider this situation where we have a magnetic conductor, a perfect magnetic conductor, and a perfect electric conductor. And then we could take the quantized version. So what we do is we just put an expectation value over here, and then 1 over IH bar. And what happens is that this is equivalent to, this equals the dyadic. That we calculate the full E&M dyadic, which is given, and in the equivalence limit, it gives us stress energy tensor. And then this is given by the trace of this function, which takes into account the TE and the TM modes, the TM modes and TE. So in the limit that's a perfect conductor, we get a pretty nice expression. We're able to, there's like a volume integral over here. So we have force, the force density. We take the volume of it. And then that's pretty much, we could say there's a volume over this, over A. And then the plane, the directions in the plane, we could cancel these. And then we have a delta function coming from this limit, this perfect conducting limit, and we get a nice finite expression. So in the Casimir effect, we could, things are simpler in the conducting limit and the very weak limit. And what we get when we take the trace of this, we get some divergent terms. And then we get some, which we could kind of, we could say that these are, these don't contribute to the interaction, and we get an interaction term, and we get some reflection coefficients given by these terms, which encode the material property. So what happens in perfect conductors is the electrical coefficient, the electrical reflection coefficient goes to 1, the magnetic goes to -1, and then, or I should say this, this is a bar. Goes to -1, and then vice versa. So we get term that has -1 in here, -1. And then over here, this is still -1, -1. So then when we calculate the pressure, we get this showing up. And this is just resembles the Fermi-Dirac distribution. And then we get a -7, -7/8, and then this term, which is which is common. And then when we do the electrical condense, we'll see that what we get is our E showing up and our A bar showing up. So the reflection coefficient bar is just -1, and that gives you squared, gives you 1. And then this is just 1, and squared obviously gives you 1. So what we're left with is we're left with this integral, obviously excluding the divergent parts, so neglect these, only considering the interaction term, and we get something that looks like a Bose-Einstein distribution. So so what does this mean? Okay, so there's a lot of interpretation here that needs to be filled in, and especially because this green static also takes on negative values too for the repulsive cases. So that is, all these things are a need for interpretations. We have them. Also, where's the 7/8 coming in? That's also pretty mysterious. Between we call this the Boyer cavity, electrically conducting, and a perfect magnetic conductor, compared to the perfect electrical conductor and the perfect electrical conductor. So, yeah, is there any questions at this point? No. Okay. Like I said, I was planning on doing an iPad talk, which I think would have been much more interesting. I have some time. I could go over the derivation of the multiple scattering formalism, because I really think it's beautiful, especially using the stress energy tensor, going from computing things with stress energy tensor, and looking for the finite contributions coming from this term rather than the multiple scattering formalism, where we could just take this term and extract it exactly. Hello? Yeah?
I had a quick question, actually. Back when you were showing these repulsive and attractive regions with the polarized atom above the ring, what was setting the length scales in that problem? What physical quantities set the location of the minima and the width of the local well?
Okay, so the length scale. So we took. Sorry, this is actually the ratio of the height over the radius of the ring. So so yeah, so this is maybe that looks like 0.6, around 0.6. So yeah, so when the height is 0.6, the radius of the ring, it will give us this. So below, so pretty much the repulsion, how high the repulsion is, depends on the region of repulsion depends on the radius of the ring. Is that what you're asking?
Yeah, I think so. It just seems like that 0.6. Perhaps there's no other length scale in the problem other than the width of the ring. Like it just seemed like such a interesting place for a turnover, right? I was sort of expecting even another like another length to come into play.
Yeah. So okay. So so we're working in a regime where the radius of the ring has to be a certain needs to be a certain length for this to work. So yeah. I'm not sure.
Interesting. Yeah.
I think you might get repulsion no matter what the length of the. I mean, if it is in just nanometers, that's it. I don't think there is. I don't think the repulsion is special. I mean, the calculations simplify working in the relativistic limit, but yeah, I think just any type of just in the nanometer scale.
Okay. Cool.
Yeah.
Thanks.
Yeah. Did I go out again? Yep. Oh, hey. Hello? I thought I was
We can hear you.
okay.
It's okay.
Yeah, I don't know. Was I don't know if I was gone the whole time or not. Yeah, thanks for coming. Does anyone have any questions? Really, I mean, if you have anything, you could. This was supposed to be a learning experience for me. Yeah, I signed up because no one was signing up for these meetings at one point. There was so many empty spaces, and then so I figured that I didn't want to just waste space, like have no one present. Been foolish to waste the opportunity. So it's not too much.
Here, can I ask just a really basic question from someone who doesn't know much about the Casimir effect?
Yeah.
Can you just give some intuition about why it's so hard to find a scenario where it's repulsive?
So there is only so I guess these scenarios just kind of it pops up. So it's not very difficult. Okay, so what was so I guess this scenario repulsion was pretty new and interesting. But this has been known for a while with van der Waals force. So pretty much materials, the Casimir repulsion either comes from like magnetic or electric. The permittivities are like a mixture of electric and electromagnetic permittivities. So some intuition. I have no idea. That is why I think studying this is so fascinating. So as of now, we see that the two plates kind of behave, have like this Fermi-Dirac distribution. So they kind of behave like fermions, and then the electrical conducting kind of behaves like bosons. The anisotropy, I really have no clue. No intuition. I like that's how it is. Yeah, I think so. That's why I'm interested, because I think really, because now we have some situations where, okay, we're getting all these different situations where repulsion plays a different role. You know, we're getting the disc, the ring, the plate. Can we conclude something? So it's not just anisotropy, but there needs to be an aperture involved too. Yeah. So this is pretty skeptical. I don't think this is. I don't think this is accepted, but this is the only result, that there is also a sphere. So the self energy of the sphere. So if you have like a conducting sphere, this will be repulsive. But I think there are various reasons. I asked my advisor about this one time because I didn't really understand it, and then he said, yeah, don't worry, it's not. This is pretty skeptical, but there is no other calculation saying that the self energy of the sphere is not repulsive. Yeah. So.
Okay, thanks.
Yeah. Yeah. So I don't know if this goal is. I mean, there's like a lot of parameters, so you can't really. I don't know if you could do something like field lines. You know, have some field line interpretation of what's going on here, but yeah, there's something happening. Yeah, especially with this. Yeah, so that's why I kind of figured this would be a good place to present, because I mean, I'm interested in like the fundamental aspects, like what is, you know, like what's actually happening in the quantum vacuum, like what, you know, these photons in particle physics, these virtual photons, I guess they provide a nice explanation. But like really what's happening at a quantum level, like in the vacuum state, clearly something's happening. We see this is observed, but what, I don't know. But yeah, I mean, this also has applications, like we saw the molecular machines for nanotechnology. These come into play. So yeah. Any more comments? Anything to add? Anything interesting to share that you might have research on? You might know something. And this was kind of fun. Supposed to be something fun to do, a fun time. So. Yeah. All right. Well, I'm going to end this meeting then. Thank you guys for showing up. This really helped me put my writing the paper into perspective. So yeah.
Thank you.
Yeah. Thank you. Okay. Have a good weekend.